grade 11 mindsetters, welcome to today's physical sciences show. Today we have a special revision lesson on gas law calculations. We have selected highlights from lessons shown earlier in the term to help you revise. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. You can also download the notes for today's show from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Let's move on and have a look at our questions here, where we can try and improve our knowledge and our skills in solving some of these problems. Question number 1, okay? It says here, express the following in Kelvin temperature scale. And the first one that we have is 25 degrees Celsius, and the second one is 0 degrees Celsius. Now, let's come up with a formal way of doing this. When we talk of the Kelvin temperature scale, whatever temperature we're talking about is the unit of measurement is the Kelvin. So we use capital letter K for it. And the symbol for Kelvin temperature is capital letter T. Whilst for Celsius temperature, okay, what we have as the symbol for it is small letter t. And of course, we measure these in degrees Celsius. Now, converting from Celsius temperature to Kelvin temperature, we will always do it in this way. So Kelvin temperature, which is T, will always be the Celsius temperature plus 273. That is your absolute zero temperature. Okay? And that will give you your temperature in Kelvin. Now, what does it mean then for the questions that we are having? The first one is 25 degrees Celsius. So changing that into Kelvin temperature will be Kelvin temperature equals Celsius temperature plus 273. And that is Kelvin. So that will be equal to small letter t, 25 degrees Celsius plus 273 Kelvin, as a number now. And together they give us 298 Kelvin. So that is 25 degrees Celsius in Kelvin. Okay. And the second one is 0 degrees. So number B, we're converting 0 degrees Celsius into Kelvin. So T will be equal, capital letter T will be equal to small letter t plus 273. This should be easy to do. So we've got 0 plus 273 Kelvin, and that will be, so when I said Kelvin, I meant that when you have added everything together. So that gives you 273 Kelvin. Now, this is 0 degrees Celsius. That's right. This is 0 degrees Celsius. So it means that 0 degrees Celsius is 273 Kelvin. Now, this is what we call our absolute zero. Okay, this is absolute zero. Okay, now, okay, this means, I think I need to re-explain what I'm saying here, because I didn't say it as correctly as I should. Now, look, what I'm saying here is that it means that 0 degrees Celsius is not absolute zero in terms of temperature. Now, the absolute zero would mean it is the minus 273. From 0, you need to go 273 to the left to find absolute zero. So minus 273 becomes the absolute zero. So minus 273 Kelvin. is the absolute zero temperature. Okay, absolute zero temperature. Okay, right. Now moving to the next one. Under what conditions does the behavior of a real gas deviate from that of an ideal gas? Explain your answer. Okay? Under what conditions will we see the behavior of a real gas? You know, saying to us, I am not an ideal gas, I am real, I exist. So which conditions will tell us that we are not dealing with an imaginary gas? Now, we said earlier on that when you have very high pressure, you are bringing the molecules very close to each other such that the intermolecular forces between them become effective. And you have got low temperature, okay? Low temperature. These two conditions will make your real gas to deviate, to say, no, I am not ideal. I am not imaginary. I exist, so I will behave in a different way if you have those conditions there. Right. 4 main properties of an ideal gas. Let's just write 3 that are more logical. The first one, we said that these molecules of an ideal gas have got mass but occupies no volume. Okay? So those molecules have mass and occupy no volume. All right? So the molecules have mass but occupy no volume. Occupy no volume. And 2, remember we said there are no intermolecular forces between them. We say with an ideal gas, with this imaginary gas, the molecules do not attract each other. So no intermolecular forces between the molecules. No intermolecular forces. There is nothing like that. Okay? Molecules, okay, occupy no volume, no intermolecular forces between them. And what else? What else? Who can think about the other one? Okay, quickly, molecules have mass but do not occupy volume, no intermolecular forces between them. And one very important condition or property or characteristic of an ideal gas, the collision or collisions between molecules. Between molecules and between molecules and the sides of containers. And the sides of the container are completely inelastic. So these collisions are completely inelastic. I mean completely elastic. Oh, sorry, what am I saying? Completely elastic. Now, remember what we mean by collisions being elastic? Remember that? We are saying that the kinetic energy is conserved. It does not change in the process of collisions. Kinetic energy is conserved. That's what we mean by collisions being elastic.
Okay guys, I hope you are enjoying this revision session. If you need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, but don't go away. We'll be right back. Welcome back, guys. We have some great news to pass on to you. We will be bringing you winter school from the 30th of June till the 20th of July, starting at 10 a.m. every weekday. To get the full schedule, visit our website, learn.mindset.co.za, and look for the winter school link. Join us. It's going to be a lot of fun. But now it's time to get back to the lesson.
Let's move on, and now we're going to look at exemplary questions, questions that you can expect from question papers, and something that can help you practice. You see, that's how much Learn Extra loves you, gives you practice questions so that you can actually get ready for your exams and other things. Let's just have a look at this one here. The first question is question number 1. We're talking about, let me just read it first. It says 1,000 cubic centimeters of gas at a pressure of 100 kilopascals is kept in a sealed container at 25 degrees Celsius. Okay? It continues to say the volume of the container. So the volume of the container is increased. Oh, so volume is one of those quantities that is fiddled with here, such that the pressure of the gas decreased, okay, to 80 kilopascals. This sounds more like Boyle's law. Okay, so I'm trying to think of which equation, which formula am I going to use. The way I'm reading it, it sounds more like Boyle's law. I'm reading volumes changing, leading to pressure changing from one value to another, but I'm told there's a temperature here. But let's read and find out about this temperature. It says, when all these things are happening, the temperature remains constant. Now, this is definitely Boyle's law, because with Boyle's law, we keep temperature constant, we control that variable, and then check the others. We control the temperature, we control the quantity. We don't add or remove anything from the quantity of the gas. So let's see how we're going to deal with this then. So this means that if I'm to calculate for the volume, okay, calculate the volume of the gas. If I'm to calculate for the volume, it means I would say pressure. Oh, let me just do it this way, writing down what is given to me. P1 is given to me as 100 kilopascals. P2 is given to me as, it changed to 80 kilopascals. And V1, I was given 1,000 cubic centimeters. And V2 is what I need to find out. So that's what I need to calculate for. Right. Now, I use Boyle's law because this is based on Boyle's law, which says volume 1 pressure 1 times volume 1 should be equal to pressure 2 times volume 2. Now, I think every science teacher that speaks to you always say this, that if you have got a formula to work with, the best thing to do is to substitute into that formula without making what you are looking for the subject of the formula before, because that makes sure that even if you have or you make a mathematical error along the way, at least you have all the marks in terms of the substitution. So I will continue to teach you like that and say substitute. I'm told here P2 is 80, so I write here 80 times V1. It's given to me as 1,000. Okay, this should be equal to P2 is given to me as 80 times V2 is what I'm looking for. All right, so I would have that. So at this point, I did that so that I can get marks for that substitution. And of course, I would have earned a mark for writing down the right formula to use for this calculation. Therefore, from there, I would know that V2 equals, what is P1 here? Oh, made P1. I think we made a mistake with P1. I'm seeing my mistake now because I'm looking at that. P1, it's 100. So this is 100 kilopascals. Okay, so that is 100 kilopascals. So we actually made a mistake there. So this 80 here should be 100. Okay, that's my P1. That's my P2. So that's what we have. So V2 will be equal to 100 times 1,000 divided by 80. And what is that? So let's work it out. We do have a calculator here. Work it out. So we've got 100 times 1,000 divided by 80. What do we get? 1250. Okay, so this is 1250 what? Cubic centimeters. And it makes sense because we have actually reduced pressure, so volume had to increase. That is Boyle's law. That's what it says. The two are inversely proportional to each other. That is the kind of relationship that they have. So that's why I like science, because once you understand the rule, when you make a mistake in your calculation, you check your answer against the law itself and you see, hey, something is wrong here. Suppose I got the volume to be decreasing as the pressure decreased. Something would have gone horribly wrong in my calculation, because then that would not be supporting Boyle's law. So that's one thing good about science. Right, now moving on to the next one. Okay, we're looking at question number 2. Question number 2 says, an amount of gas is heated under constant pressure. Constant pressure, this sounds more like Charles's law. Okay, Charles' law sounds more to what I'm reading here. So that its temperature increased from 25 degrees Celsius to 30 degrees Celsius. The volume of the gas at 30 degrees Celsius is 150 cubic centimeters. What was the initial volume of the gas? So I need to find V1, initial volume of the gas. Because I am given V2, I am told V2 is 150 cubic centimeters. All right. But then, what other variable has been given to me here? I'm given temperature. I'll use small letter t for it. And those of you who remember last week's lesson, you remember that you use small letter t there for gases in talking about temperature when you're talking about degrees Celsius kind of temperature. Because with the Kelvin temperature, we use capital letter T. So I'm given this temperature in degrees Celsius. So I'm told that T1 is 25 degrees Celsius. T2 is 30 degrees Celsius. But it is very, very important for you to know that Charles' law speaks about absolute temperature. Absolute temperature. Okay, so we're talking about absolute temperature. So if you are given temperature in terms of the degrees Celsius, you would know that you would need to convert that into the Kelvin temperature to be able to do your calculations correctly. For your calculations to be correct, you need to convert this. Therefore, down here, it means I would say my T capital letter T, which is absolute temperature, will be 25 degrees, will be 25, so we don't want to even see degrees there. That will be 25 plus 273 Kelvin. So what I have as my T1 is 298 Kelvin. The same thing this side. T2 would be 30 plus 273. That is how we convert to absolute temperature. So T2 equals that. So that equals 303 Kelvin. Okay? So these are the two values of the temperature that we are going to use here, because, let me emphasize it, we can't use the degree Celsius scale here because the law is based on the Kelvin temperature. So then we will be able to say pressure 1 over volume 1 will be equal to pressure 2 over volume 2. What am I asked to find out? I'm asked to find what the initial volume is, V1. I have V2 and I have T1 and T2. So let's substitute into this all these values. Okay. P1, what did I do here? This should have been T1. Sorry about that. I think I messed up here. We're talking Charles' law. So these are your temperature 1 and temperature 2. Okay, good. So now what is your temperature 1? Temperature 1 is 298 divided by volume 1 is what I am looking for. Temperature 2 is this one here, 303 Kelvin divided by volume 2. What is volume 2? We are told of volume 2, 150 cubic centimeters. So we put that in, 150. All right, therefore, my V1 equals, can cross multiply now, 298 times 150 divided by 303. I am not bound to use this step. I'm just helping you. This step here is not really necessary for me. I can go straight to the answer, but I'm just showing you, especially those that are battling, to see where all this come from. So let's see, with the use of the calculator, what the answer is going to be. Okay, so this is 298 times 150 divided by 303. And what is the answer? The answer works out to be 147.52 cubic centimeters. So 147.52 cubic centimeters. Oh, what a cubic centimeter value is that? So cubic centimeters. Now, that is the answer for that one. Emphasizing it again, because I know it always evaporates out of our mind most of the time. When you're dealing with Charles' law, temperature should always be in absolute values, which is the Kelvin temperature scale. Convert, if it's given to you in temperature, in degrees Celsius. Convert from degrees Celsius to your Kelvin temperature. Okay.
Sorry, it's Landis was saying, AP, can you please ask for me, aren't we supposed to convert V1 into DM3?
Oh, okay. All right. It's not necessary when you're dealing with these equations here. In both Charles and Boyle's law, with that volume, it's not necessary to change it. Why? Because you're changing it by the same factor. Let me just show you with the first one here. Say you're looking at this one here of calculating for the for V2, the very first question we looked at. You would see that this is the volume. This is your volume. It is in cubic centimeters. And your volume this side would also be found in cubic centimeters. Why? Because even if you change this one by, you convert this into cubic dm cube, you're going to multiply that by 1,000, so a factor of 1,000. And let me, for the sake of space, use just you convert this by actually dividing by 1,000. I mean, dividing by 1,000, which will be dividing by. I made a mistake here, so let me take that out. So you are dividing these cubic centimeters to change them into dm cubed by 10 to the power 3, by 10 to the power minus 3, all right? Or what am I doing here? Let me just get this one right. Okay, so you either dividing by 1,000 or multiply by multiplying by 10 to the power minus 3. This is the same as dividing by 1,000. This side, you are also going to multiply by 10 to the power minus 3. So what is basically going to happen is that because this is an equation, this equals that. And this is multiplication and that is multiplication. If I have 10 to the 3 on the left and 10 to the 3 on the right, I can actually cancel that out. And that is the reason why actually converting is not so necessary. This is the same thing with pressure. If you want to change pressure from kilopascals to pascals, okay, what are you going to do? You're going to multiply both sides. You multiply both sides by 10 to the power 3. So even this side is going to multiply by 10 to the power 3. This is when we're talking about pressure now. And because 10 to the 3 is both on the left and on the right, you can actually do away with that. So that conversion becomes, does not affect your calculation. So that's why you don't have to go to the SI units as such. But when you come to Charles's law, the conversion from the degrees Celsius to Kelvin becomes necessary. You have to do it. Why? Because there we are not multiplying by 273, okay? We're not multiplying by 273 or dividing by 273. So that in both cases, you can say you have got a common factor. But what are we doing there? From T, we add. So when you're adding, the reciprocal or the additive inverse of adding is minus. You can only deal with those. If you have got division and multiplication, okay, the two are reciprocal of each other, so you can play around with them. So with the Charles's law, when it comes to temperature, you can't say, I can work in degrees Celsius. You always have to move from degrees Celsius to Kelvin.
Okay, quickly
Yeah.
before we go to the challenge question,
Yeah.
two questions relating to that same question.
Okay.
Pomelo says, how do I know which one is P1 and P2? And Karabo Selemela saying, I think you've made a mistake. You substituted P1 twice. It's 1,000.
Oh, okay. I think Karabo didn't see what's happening here, but just a quick correction for Karabo. Karabo, if you look at these here, the P1, the pressure one, was 100 kilopascals, and the volume one was 1,000 kilopascals. So there is nothing wrong there. Maybe because we used the 100 and 1,000, you didn't really see the other zero there. So this way for pressure, 100, volume, 1,000 cubic centimeters. So that's what was happening. So there's nothing wrong there. You can continue with that calculation. All right.
The other one, how do you know which one is P1?
How do you know which one is P1? That is definitely having to do with how you read your question. You need to read the question. You need to know, the question will tell you. Let me just put it that way. The question will tell you that the first pressure was this. They won't say first pressure was, they will tell you maybe pressure changed from this value to that value. So this value then becomes your P1. That value becomes your P2.
I think it's time for a break now. Don't go away. We'll be right back. Welcome back from the break. Let's not waste any time and get straight back to today's revision lesson. Over to you.
Let's look at the questions now. Question 1, all right? In the notes that you're going to receive and download from the Mindset web page, there is more notes on what I had. The notes, the latter part of the notes will be talking about the ideal gas equation, okay, which will be necessary for you to know. A certain mass of carbon dioxide gas is sealed in a 200 cubic centimeter container. The gas exerts a pressure of 100 kilopascals on the sides of the container at a temperature of 0 degrees Celsius. Now, calculate. Calculate number A, the number of carbon dioxide gas moles present in the container. Number of moles of the carbon dioxide gas present in the container. Now, if you check on what is given to us, let me just list them on the side here. We are given the volume in which the gas is kept. The volume is 200 cubic centimeters. And we are also given the pressure that the gas is at. So pressure is 100 kilopascals. All right? We are also given the temperature in which the gas is kept. Okay? We are told that this is at a temperature of 0 degrees Celsius. Now remember that we don't use the degree Celsius scale, we use the Kelvin scale. So from 0 degrees, converting, you always add 273, and that gives you the Kelvin. So you've got 273 Kelvin. All right, so that is your temperature. Okay, now, number A, we are to calculate the number of moles present in the container, given all those information. Now, A, if you look at the information given to you, the equation you are to use will be the universal gas equation, PV equals nRT. Why am I using that? Because I am given the pressure, given the volume occupied by the gas. I need to find out how much of the gas is there, and that is given to me. It's a constant, and that is also given to me. All right. Now, also, when I use this equation here, or this formula here, I need to know that always the pressure is measured in pascals. This is the SI unit of pressure. The volume has to be in cubic meters. That's very necessary for me to know. Of course, N should be in mole, okay, measured in moles. And R is the universal gas constant, which is always known to be 8.31 joules per Kelvin per mole. Okay, per mole. Allow me to write like that because I don't have much space. And the temperature must always be in Kelvin. Okay, so this is very important. Why do I say so? Let's come back here. You will see that you are given volume in cubic centimeters. You have to convert. You are given pressure in kilopascals. You have to convert to pascals. So let's work it out. 100 pascals, kilopascals in pascals, you need to multiply by 10 to the 3 so that you come back to pascals. Then multiplied by volume, you have got 200 cubic centimeters to cubic meters. Because if I move from cubic centimeters to cubic decimeters, I'll divide by 1,000. If I therefore move from cubic centimeters to cubic meters, I'll have to divide by 1,000,000. That is 10 to the 6. So it means this 200 cubic centimeters is 200 divided by a million, which is the same as multiplying by 10 to the power minus 6. This must be equal to my N, is what I'm looking for. R is 8.31. What is my temperature? Times the temperature, which is, if the temperature is 0 degrees Celsius, it will be 273 Kelvin. Okay, so you work this out. Let's just work it out. Where is our calculator? So I've got here 100 times 10 to the 3 times 200 by 10 to the power minus 6. Okay, what does that work out to? It works out to just 20. So all this in the left works out to 20. And the right hand side, I can simplify it. You have got n times. Okay, so n times what? You've got here 831 times 273. Okay, so 8.31 times 273, the Kelvin temperature. You have got 2268.63. 2268.63. Okay, comma 63. Now, the number of moles equals, all right? So that will be equal to 20 divided by this, okay? So 20 divided by 2268.63. And what is that? That gives us 8.82 by 10 to the power minus 3. 8.82 by 10 to the power minus 3. Okay, what is this? This is moles. Okay, this is moles. So I have found now the number of moles present in that container. Let's come to number B and see what number B wants us to do. Now, number B says, calculate the mass of the carbon dioxide gas in the container. Now, for me to get the mass, what am I going to do? Now, I have the number of moles of the gas now from the gas equation. I need to move to the mass. To move to the mass, the equation or the formula that helps me to get the mass is this one. That says number of moles is equal to given mass divided by molar mass. Okay? So this equation here would help me because I am going to substitute this value for the number of moles. And I need to know what is the molar mass of this gas. Now, the molar mass of the gas, let's work it out on the side. Remember that I said if you are to work out the molar mass, you will have to look at the gas, and that will be equal to, for carbon, you look at your periodic table, you get the molar masses from there, the masses of each atom that is involved in that particular substance. For this substance here, we've got carbon dioxide, CO2. For carbon, you check your periodic table, it is 12. For oxygen, you check your periodic table, it is 16. So you work it out, this is 12 plus 2 times 16 is 32. This gives you 44. Now, this is the molar mass of carbon. So it's 44 grams per mole. For every mole of carbon, we will have a mass of 44 grams. That's what it means. Therefore, coming back here and finishing off my calculation, I will then substitute the number of moles here with what I calculated here. It's 8.82, 8.82, so 0.82 times 10 to the power minus 3 will be equal to, mass is what I'm looking for. Molar mass I have calculated is 44. So what does this mean? Therefore, the mass of carbon will be equal to 44 times 8.82 by 10 to the power 3. So let's go there. I still have that value there. I'll just say multiply by 44. Okay, multiply by 44. And what do I get? 0.39 grams. 0.39 grams. So that is the mass of carbon that I have. Okay, I mean of carbon dioxide that I have in that container. Right, going back to the next question. Okay, question number 2. Question number 2 says, a certain gas at a temperature of 20 degrees Celsius and a pressure of 80 kilopascals is kept in a container of 250 cubic centimeters. The gas is now compressed such that its pressure decreases. Okay, oh, this should have, let me just change it for you now. Bit of a mistake here. Pardon me for that. So it is compressed. It can't be compressed from 80 kilopascals then to 130. If it is compressed, that pressure must get less. So compressed to 60 kilopascals. Okay, so remember that. We're going to use that one instead of the 130. The temperature of the gas increases because of what has happened, because of the compression. It increased from 20 degrees Celsius to 45 degrees Celsius. Now, calculate the volume of the gas after it has been compressed. Now, let's look at what is given to us quickly. You've got pressure 1, which is 80 kilopascals. You've got volume 1, which is 250 cubic centimeters. All right? Then you have your temperature 1, which is 298 Kelvin. And that is 20 degrees. I mean, that's 20 plus 273 to give me 298. And then you have the second part here. You are told that it is compressed such that the pressure comes to 60 kilopascals. All right? And then when that happens, the temperature increased from 20 degrees to 45 degrees. Okay? And what is that? That will be 45 plus 273. What do you get? That gives you 318 Kelvin. Okay? And from there, then we can work out our problem. If you look at what you have here, you can actually think of what law you are going to use. Let's just quickly have a look at it. P1 V1 over T1. This is the combined gas equation. Should be equal to P2 V2 over T2. All right. Over T2. So I can begin to substitute here. P1, I've got 80. I've got 80 times. V1 is 250 divided by. T1 is 298 equals. P2 is 60 times. V2 is what I'm looking for, and T2 is 318. Now, come on, you take out your calculators and we work this out together. All right. Now, 80 times 250 divided by 298. What do we get? The answer is 67,11. 67,11 equals. Okay, And then this side, I've got 60 divided by 318. 60 divided by 318. What do I get? I get 0,188. 0,189. Okay, 0,189. 0,189. What is the quantity I'm looking for? Is V2. Therefore, V2 equals 67 divided by 189. 0,189. Okay, so let's work it out here. So 667,11 divided by 0,189. 189. What do I get? Let me do it again. There's a mess here. 67,11 divided by 0,189. And the answer is 355,08. 355,08. So 355,08. Okay. Now, let me check here. Okay. Right. So you have, we need to work this one out quickly. I think there's something that went wrong here. We shouldn't be getting that answer. Anyway, let's go back to it. Let me see. I think I still have some time quickly to work on it. Let's just go back to it. There is something that went wrong somewhere here. So let me just quickly erase this, and then we work it out quickly. Okay. Right. Now, from there, it's 80 times 25 divided by 298. So 80 times 250, not 25, 250 divided by 298. 298, and let me just ascertain that is 67,11. Okay, so 67,11 equals 60 divided by 318. Okay, quickly, 60 divided by 318. 60 divided by 318. What is that? 0,189. 0,189. 0,189 V2. So why are we not getting? Okay, so then this would be equal to V2. Okay, therefore V2 equals 67, comma, okay, let's go back there. 67, comma, 11. We divide that by 0,189. Why do I still? Okay, that's fine. Then it gives us 355,08. 355,08. Okay, 355,08. 355,08. This must be cubic centimeters. So that is the way you were supposed to work out this question here. Now, for something for you to always note is to make sure that your Kelvin temperature is the scale that you are using all the time, nothing else. Yes, we have actually found it. In fact, the calculation itself was actually making me think, no. That's not the way it should be. But then let's go back to it. Instead of changing this one to 60, the word here should have been saying that the pressure increased to that, because when you are compressing something, the pressure of the gas actually should increase. So that's where I was actually getting it a bit wrong there. So the pressure increased or increases to 130. So 130 stays, and down here, thanks to a mindset that helps us to see it, is it a she, Abram? Somebody.
It's so many of them. It's so
help
many
us
of them.
to see where this where the mistake is here in our calculation. So you would see here that instead of, when you have 20 degrees Celsius, that will be 293, not 298. I'm used to the 25 degrees Celsius. This is 20, so that should be 293. That side, that stays, but what should change? This must change to 130. Okay, so that is 130. Then when you work out this, it will then begin to make sense, because it will show us that actually the volume has decreased. If you compress something inside a container, the volume of that particular substance is bound to decrease. Okay, so you work this out quickly. We worked it out this side. Let's just go through the calculator quickly. So this is 80 times 250 divided by 293. Okay, and we get 68,259. 68,259. And that equals, if you go back to our calculator, we work out the fraction this side, which is 130. You divide that by 318. Okay, 318, and your answer is 0,409. 0,409. 0,409. And then you work this out. This is V2. Therefore, V2 would be equal to 68. Okay, it's going to be 68,259 divided by 0,409. You would see that I am very consciously keeping 3 decimal places, because I'm not yet down to the answer. So 166,89. 166,89 cubic centimeter. Yes, this volume here makes sense, because we are from a volume of 250 cubic centimeters down to a volume of 166,89.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get the notes and to watch the videos from the term. Goodbye.